Hello everybody, I'm Dr. Alexander. I'm going to show you a series of demonstrations called Fun with Gas. Have you ever had fun with gas? Did you ever have gas problems? Anyway, I have some gases here. Can you see what that says? That's the only way I can tell what's in it. It's hydrogen gas, and this is also hydrogen gas, and this is hydrogen gas, and then this is oxygen gas, and this is oxygen gas. And let me show you something first before we get into this experiment. Can anybody identify what that is? Oh, somebody said it's butane. It's not butane. These are styrofoam balls glued together. But you were close. It's a model of a molecule of butane, and the black balls represent carbon atoms, and the yellow ones represent hydrogen atoms. And in this one, there are 4 carbon atoms and 10 hydrogen atoms, and so we say the formula is C4H10. That's the formula of butane. Okay. Now I have another one here. This is a molecule of propane. It's got 3 carbon atoms in it and 8 hydrogen atoms, so it's C3H8. And this one's kind of interesting because if you put it down, it looks like a little dog, doesn't it? Doesn't that look like a little dog standing next to a fire hydrant? And this dog is unusual. He can use either end. Okay. Now these are called hydrocarbons because they have hydrogen and carbon atom in them, in the molecules. And I have a model of the simplest of all the hydrocarbons. This one only has 1 carbon atom and 4 hydrogen atoms. And this is called it's called methane, and the formula is CH4. And this is the one that's most familiar to everybody because it's found in natural gas. So when you eat your home with natural gas, you're burning this in El Paso, and they burn natural gas to make electricity. And by the way, when you eat beans, you make this gas. And has anybody ever discharged the gas to the atmosphere? Yes, you have. Okay? And this gas, by the way, is flammable. And I know people who have lit their own gas. I've never done that. I heard a friend of mine did that one time. He was taking a shower and he knew that the gas would burn, and he got out of the shower and lit it, and then he found out he should be wearing clothes before he do it because he got burned. That's a true story, by the way. Okay, now what I'm going to do is demonstrate something everybody's familiar with. By the way, this is a lighter here. Can you see there's a liquid in there? And that liquid is actually butane. Butane is really a gas at normal pressure, but if you increase the pressure, you can liquefy it. So that's butane gas under pressure. And I can't light this now because the wheel is missing, but I have another one here. And the thing is, you can't see it as well because it's colored, but it's the same liquid that's in this one. And if you open this valve, the gas will come out. And if I turn this wheel at the same time, we get something known as fire. Okay? So that's a chemical reaction involving butane burning in air. And in the process, all the carbon atoms in the butane end up in carbon dioxide, and all the hydrogen atoms in the butane end up in water vapor. So that's what we're making in that flame right there. Okay, now what I have here is a candle. The candle's made out of solid hydrocarbons. See, if you have hydrocarbons that have 4 carbon atoms in them or less, they're gases at normal pressure and room temperature. If you have more than 4, then they become liquids up to about 22 carbon atoms, and then they become solid. So this is a mixture of solid hydrocarbons. But all hydrocarbons have something in common. They're all flammable. And so I can actually light that wick, and the vapors come off of the wick and they'll start burning. Same kind of reactions occurring. All the carbon atoms in there ending up in carbon dioxide, and all the hydrogen atoms are ending up in water vapor. Okay, now what I have here is a wooden splint. Now a lot of people think that wood burns. You probably do, don't you? Well, it doesn't burn. Let me show you. I'll stick it in that flame. You tell me if it catches fire. Did it catch fire? No, I stuck it in the flame. But I have something, so wood itself doesn't burn. But I have something here that burns. It's a hydrocarbon mixture. And if I stick this in the hydrocarbon mixture and stick it into the flame, then you see it does burning, but that's the hydrocarbon mixture burning. Okay? Now what actually happens is this. If you heat wood, it decomposes and changes into other chemicals that burn. It changes into a gas that burns, and it changes into a solid that also burns. And let me see if I can demonstrate that. I'll put it over the flame. I'm not going to touch the flame. I'll just put it over it, and the flame's going to heat it, and it'll start giving off a gas, and now the gas is burning. You see that all right? Okay, then if I blow it out, can you see that there's a solid burning? That's charcoal. Charcoal is a solid that also burns. It glows when it burns. Okay, now the reason why this was burning is because there's oxygen in the air, and that's combining with the hydrogen atoms and the carbon atoms to form the water vapor and the carbon dioxide. So you have to have oxygen in order for that to burn. But the air is only about 21% oxygen. It's mostly nitrogen, and nitrogen does not support combustion. But actually nitrogen reduces the activity of the oxygen in the air to make it safer. And I have here a bottle of pure oxygen. Let's see where it is. There's a bottle of pure oxygen there. And I'm going to demonstrate that things burn a lot better in the pure oxygen than they do in the air in a minute. But I'm going to show you something else first. So I'm going to light this stick, and I'm going to blow it out until it's glowing. See if it burns better. See if it glows more brighter. See if it glows brighter in the oxygen. This is pure oxygen now. So it should burn better in that there, I think. Let's see if there's any evidence it burns better. Did it burn better there? Yes, it caught fire, right? Now, a demonstration I used to do, I used to do this for elementary schools, and one time I took a cigarette and I lit it so it was glowing, and then I stuck it into the oxygen, and it burst into flames. And so I said, son of a gun, that'd be a good way to stop smoking, because these cigarettes burn in pure oxygen. So if you had pure oxygen in the air, you wouldn't be able to smoke. And I got a letter from a kid, and he said, and this is a true story. He said, he was a fifth grade kid, and he said, I wish we had pure oxygen in the atmosphere because my daddy would stop smoking then. It's a true story. Okay? I went to one of our local chemical supply houses called Albertsons, and they have the solid form of carbon dioxide. Can you see it? There's a name for that. It looks like ice, but it's absolutely dry. What would be a good name? Oh, how about dry ice? So dry ice is the solid form of carbon dioxide, and it's much colder than regular ice. This is actually minus 78 degrees Celsius, or about 125 below zero Fahrenheit, and you can't warm it up. If you try to warm it up, all it does is sublime. Turns into the gas directly. It doesn't melt or anything. And so liquid CO2 doesn't occur at normal pressures. You'll have the solid form and the gaseous form. Now this bottle here, let's see, does that say CO2 on it? That's really not true. It's got air in it. But I'm going to put dry ice in there, and the dry ice is sublime. By the way, you know how this is kind of dangerous to hold it. You know how long you can hold it? That's long enough. I've learned over these years how long you can hold it. If you hold it too long, you get frostbite. Can you see you're getting a little bit of a fog in there? That's actually the moisture in the air condensing out. And now it's subliming. Now CO2 is heavier than air, so whenever it sublimes, it gradually fills up and comes out the top. Now the thing is, CO2 does not support combustion. So let's see if I light this stick. In fact, we use CO2 to put out fire. See if it'll put out the fire. You ready? You see it go out? Now where's my oxygen? Is this the oxygen? No, this is the oxygen. Is this the oxygen? Yes. So if I want to relight it, I can do over here. If I want to put it out, put it there. Relight it here, put it out here. Light it here, put it out here. See how chemists have fun? Starting to use up the oxygen though. Okay, now the thing is, we now know that CO2 will put out fires, right? In fact, we use CO2 to put out fires. A lot of fire extinguishers are CO2 fire extinguishers. It won't put out all fires though. If you get an aluminum fire or magnesium fire and you put CO2 on it, the fire gets bigger because it takes the oxygen right out of the CO2. So, but most things will not burn in carbon dioxide. And it's heavy too. That's why I was staying in there. And I think that I actually can pour this out of this bottle down this tube. And I think it'll come out the other end. How can I prove it? Oh, I know how. I should put that fire out, right? Let's see if it does. Is that cool or not? By the way, this is a model of the carbon dioxide molecule. The carbon atom's in the middle and the two oxygens on the end, and they're all lined up in a straight line. So in dry ice, you have billions and billions of these in there, in the dry ice. It's kind of interesting why they stick together too. The oxygen atom has a slight positive charge, the two hydrogen atoms have negative charge, and in the dry ice, one oxygen atom from one molecule is attracted to the carbon atom of the next one. It holds them together as long as they're in that arrangement. Then once you disturb it, like try to melt it, it just flies apart to the gas. So that's why it's so blind, actually, because of the shape of these molecules. Propane, there's a propane torch, and I got this here. And propane is also more dense than air. In fact, it's almost the same density as carbon dioxide. So I open this valve, it's going to come out in there, and it's going to fill up from the bottom, and I can tell when it fills because it has an odor. And I can smell it when it comes out, and smell it a little bit, it won't hurt you. So now this one here, I'm going to try to show you that propane will burn. What I'll do is, and it's heavier than air, so I take the stopper out, it'll should start burning. Let's see. You see it burn? And I put the fire out. Did you get it? Okay. So it started burning, right? Hey, and now this thing will pour down this tube. You know it's flammable, right? Oh, yeah. When it gets down there, it ought to catch fire because it'll do it just like CO2. Put the fire out. Let's see if what this does. Let's pour a little bit down there and see what happens. Did you see that, everybody? That's a little bit dangerous to do, but if you know what you're doing, it's all right. This is what we were burning. So all the carbon atoms in here ended up in CO2 when they burned. The hydrogen atoms end up in water again. So all hydrocarbons burn, and they make CO2 and water. Now remember, this one was butane, a model of a molecule of butane. Now the thing is, in butane, there's more than one way of putting the atoms together. This also has 4 carbon atoms and 10 hydrogen atoms, so the formula for this is also C4H10, but it has a different structure. Can you see that? We have this one that kind of looks like a spacecraft, space or something, but this one looked like a dog with a severe nose problem. Anyway, these are called isomers. If they have the same molecular formulas but different structures, they're called isomers. And they're similar in properties, but they're different. So in this tube here, it's actually a mixture of both of those isomers, and they both burn. So that butane is actually a mixture of 2 different compounds, both of which have the same formula. Okay, now we're going to do the last part of this demonstration, fun with gas. Hydrogen is very flammable. Now what happened was, I calculated, see the hydrogen molecules look like this. Let me show you what a hydrogen molecule looks like. This is what hydrogen molecules look like. I have magnets that hold these atoms together, but hydrogen is H2, and oxygen is O2. They have, this is a model of an oxygen molecule. O2, they're just a little bigger than these. But real molecules are tiny. So the real molecules are tiny, tiny things. And in here, let's see, this one here is hydrogen. There's 100 sextillion molecules in there. Can you imagine that? 10 to the 22nd power. And they're spaced far apart. It's mostly empty space. And the molecules are moving, bouncing around in there, in between and they collide with each other, they collide with the walls of the container, and the collision of the molecules with the walls and with us creates pressure. So gaseous molecules colliding with surfaces creates the pressure of a gas. Now hydrogen gas is very flammable, but hydrogen is lighter than air. So if I take the stopper out of there, it's going to come out. So I don't want to do that. I'll have to do it upside down. Then if I light this wooden split and stick it in there, the hydrogen should start burning, but there's no oxygen inside there. I think I can put this fire out by sticking that flame in there. Let's see if it works. Let's see if that'll happen. If not, we can get another bottle, right? Ready? You see it burning at the mouth of the bottle? Do you see the fire went out on the end of the stick? And it's burning at the mouth of the bottle, and now it lit the stick in the middle. And now as it burns, I don't know if you can see it or not, but we're getting condensation on the inside of that bottle because the hydrogen is combined with the oxygen in the air when it burns, and it's making, and when the water hits the cool surface, it forms a liquid. Can you see condensation on the inside of that? There's condensation on the inside of that. Okay? Now I have an idea. Let's try this. If I take the stopper out of this other one, whoop, that's oxygen. Take this other hydrogen, take the stopper out, it should come out, right? And I should be able to light it after it comes out then, shouldn't I? Let's see if that happens. Did you see it come out? I got over there and it lit it. And that is called an explosion because the hydrogen came out and mixed in with the oxygen in the air, so when it lit, it exploded with a mild explosion. Now, if we'd done that same thing in an atmosphere of pure oxygen, it would have been a much louder explosion. Now, let's see. What's the formula of water? Anybody remember? H2O, very good. H2O. There are 2 hydrogen atoms and 1 oxygen atom in there. And what's the formula of hydrogen? H2, right? And oxygen is O2. Now it turns out equal volumes of gases have the same number of molecules. So when we had propane over here, the number of molecules here is the same as the number of molecules of hydrogen here. And that's the same as the number of molecules of oxygen in here. So equal volumes have the same number of molecules. Everybody? Now that explosion you saw with the hydrogen and oxygen, that is one of the fastest known chemical reactions. Now I'm going to try to show you why that reaction is so fast. So this is a model of the oxygen molecule. This is a model of a hydrogen molecule. And if you mix hydrogen and oxygen together like we did, they won't react at all. They'll just collide with each other and bounce off. Nothing happens. So you have to raise the temperature. But once you raise the temperature to a certain degree, then these hydrogen molecules split apart into atoms. A small percentage of them do. And then when they hit the oxygen molecule, they form a bond to one of the oxygen atoms. The other oxygen atom falls off, and then this is called an OH radical. It then strikes another hydrogen molecule to make a water molecule. And it makes another hydrogen atom. So the process makes more hydrogen atoms, so it's going faster and faster and faster reaction. And that's called a ionic type, it's called a free radical type mechanism. It's one of the fastest known reactions. By the way, what does that look like? Anybody know what that looks like? Does that look like Mickey Mouse's head? It does, doesn't it? So water molecules look like Mickey Mouse's head. And so when you're drinking a glass of water, you're drinking billions and billions of little Mickey Mouse heads. That's what you're doing. This bottle of hydrogen, I'll turn it upside down, and I'll put it over the bottle of oxygen, and then I'll turn it over so they can mix. Now, by the way, I went down the hall doing that one time. I was going from where I had the hydrogen and oxygen to go to my lecture, and I was doing this, and somebody said, "What are you doing, Doc?" And I said, "I'm trying to mix them, can't you see?" Yeah, that's really didn't happen, but I thought about it. Okay, now we should get an explosion. And since it's lighter than air, the mixture is lighter than air, I'll have those upside down. And I'll light the little one first, because that's the smart thing to do. That explosion will be not nearly as loud. Let's see. Did you hear the explosion? You want to light the big one? By the way, did you see my hand jump? There are two reasons it jumped. All the water molecules went that way and the bottle one go the other way. This illustrates the main use of this. This is used in the engines of rockets. Rockets use this when they go to the space station. They use this reaction to propel the rockets into space. And the space shuttle used to use this reaction too. So it's a really important thing, and the reason they use hydrogen rather than another type of flammable material is the light weight of the hydrogen. So they had lightweight, that's the lightest weight fuel of all the fuels. So what I'm going to do is this. I'm not going to light that one, it's too loud. But what I'll do is, this has now got air in it. I'll actually mix the air in with this, which has a lot of nitrogen in it. So I'll dilute it down so it won't be so loud. And by the way, and if it's mixed, it should be in the small one too, right? So let's see if it's in the small one. I don't think the explosions will be so loud. Let's see. See? Not nearly as loud. So let's go light the big one then. Well, anyway, that's our fun with gas. I hope you enjoyed our experiment with fun with gas. Could you tell I was enjoying myself too? Because I love to have fun with gas. I've done this hundreds of times and I still enjoy doing it. By the way, can I borrow that for a second? I got to show you my assistant. This is my assistant, Angelica Chacon. She was helping me film this. She's been my TA this semester and she's been doing tremendous work. Thank you, Angelica.